Thanks for your interest in our paper, Speech-to-Video Synthesis with 3D Skeleton Regularization and Expressive Body Poses from Baidu Research. Speech-to-video is a task of synthesize a video of human full body movements from a speech audio input. The produced video should be visually natural and consistent with the given speech, or have four main contributions of this paper. First, we propose a novel two-stage pipeline of generating an audio-driven visual speaker with full-body motions, including the face, hand, mouth, and body. Second, a dictionary of personal key poses is built that adds more dimensions to the generated human poses. Besides, we presented an approach to insert key poses into the existing sequence. Third, 3D skeleton constraints are embedded to generate body dynamics, which guarantees the pose is physically plausible. Last, we propose a modified GAN to emphasize on face and hands to recover more details in the final output video. The input to our system is audio or text, depending on what is used to train the LSTM network. We here assume that the audio and text are interchangeable using text-to-speech and speech-to-text technologies. The output of the LSTM is a sequence of human poses, parametrized by SimpleX. SimpleX is a joint 3D model of the human body, face, and hands together. This dynamic joint 3D model is visualized as a sequence of 2D colorized skeleton images. These 2D images are further input into a way-to-way generate network to generate final realistic people images. We invited two models to capture our training data, one English-speaking female and one Chinese-speaking male. We captured a total of 3 hours of videos for each model when they were reading a variety of scripts, including politics, economy, sports, and so on. In the end, we asked our model to pose for certain keywords, such as huge, tiny, up, down, me, you, and numbers. Training the LSTM and way-to-way networks requires only some videos of target animation subject reading a script. Given a video of a talking person, we first fit a human body model to each frame. Together with the extracted audio on the left-hand side, it is fed into the LSTM to train mapping from audio to human poses. On the right-hand side, 2D skeleton images of the human body model and their corresponding true person images are used to train way-to-way generated network. Finally, we manually select some key poses and build a dictionary that map keywords to key poses. Fitting a human body model to images is equivalent to detecting human key points. We use open pose, a real-time approach to detect the 2D pose of people in an image, including body, hand, and facial key points. We first attempt to take those 2D key points as a representation of our human body model and train the LSTM network that generates 2D positions of these key points from audio inputs. The results were not quite satisfactory due to the distortion of output arm and hand shown in figure. This is because this simply 2D key points human model, there is no relationship between two connected key points. They can virtually move to anywhere independently without constraints from other key points, leading to elongate or shorter arms and finger. Furthermore, at the stage of inserting key poses into existing body motion, it involves interpolating between two poses. Direct interpolating on 2D key points usually results in invalid intermediate pose that violate human articulated structure. Under these observations, we adopt SimpleX, a true articulated 3D human model. SimpleX models human body dynamics using a kinematics skeleton model to fit SimpleX human model to images. In general, we need to find optimal parameters that minimize the weighted distance between 2D projection of these 3D joints and 2D detection of the corresponding joints by open pose. We manually select key poses from the recorded videos and build a word-to-pose lookup dictionary. Again, the pose is represented as 106 SimpleX parameters. Note that a key pose could be a single frame pose or a multi-frame motion. We can insert both into an existing human skeleton video by the same approach. Inserting a key pose smoothly into an existing video sequence. A key pose is inserted into a video with a ramp length n frames before and after its insertion time points. The ramp length is only 3 here for illustration, but the real ramp length is way longer than this. Those numbers alongside vertical arrows are interpolation widths of the key pose. The weighted sum of ramp stand or end pose and key pose replace original frames in between. When we insert a pose into a video, we do a smooth interpolation in the 106 parameter space. Illustrated in figure, a key pose is inserted into a video with a ramp length n. We choose to compare our result with 4 SoTA approaches using user study. We compare to learning gesture, Lumiere Night, neural voice puppetry, and everybody dance in our user study. We get the best overall quality score compared to other 4 SoTA methods. As shown in the figure, we get 248 participants on 4 questions, which is completeness of body, the face, whether it's clear or not, the body movement is correlated or not with audio, and the overall quality. We do the Inception score comparison. We compare to Synthesis Obama and Everybody Dance by computing the score on all the frames of video generated by each model. IS is the score for generated video, and the GTIS is the score for ground truth videos. For Synthesis Obama, the ground truth is the source video of the input audio. For Everybody Dance, the ground truth is the source video to transfer motion from. And in all cases, the ground truth is the training video. It is expected that dancing videos have higher scores than speech video, and speech video have higher scores than talking head, since dancing has the most motion varieties. Therefore, we use the relative Inception score to measure similarity to ground truth. Our method outperforms the other 2 methods by these standards, meaning our visual quality is closer to ground truth. Since people don't pose exactly the same, even if the same person speaks the same sentence twice, so it is difficult to tell if our generative body motion is good or not. The only part that takes the same shape when speaking is the same words is mouth, thus we use only mouth to evaluate our motion in reconstruction accuracy. Specifically, we record a separate video of our models when they speak totally different sentences than in the training dataset. We extract the audio and input our pipeline. The output 3D joints of mouse are projected onto the image space and compared to those 2D mouse key points, detect open pose. The errors are measured by average pixel distance. Thank you. Please check our results video at YouTube.